So looking at a comprehensive solution for autonomous vehicles, that's where ANSYS is building its capabilities. So the idea is to work in a closed loop scenario. So you'll be looking at a simulation of virtual vehicles in virtual worlds, but with actual autonomous softwares. And then you have the sensors, we would have the semiconductors, we have the electronics reliability, the cybersecurity, and the software and functional safety, all taken care within the same interface. So the target of ANSYS with these new capabilities that we're going to show and the workflow that we're going to present is to make a simulation of the autonomous systems very reliable and comprehensive. So looking at autonomous systems themselves, we could look at different parts of it. It's quite a complex system. So we were talking about a few of those boxes that are in front of you now. We will start talking about how to close the loop and actually the move that ANSYS just did in order to come to that point. So the parts of environment, traffic objects and behaviors, the motion and the handling and the sensors are quite significant. That's why ANSYS just released a note that it acquired Optis. Optis is a leading company in the field of sensors and light simulation. So they have a very strong positioning already in the market, and their tools are capable of doing the what we call closed loop simulation. Looking at this video, you see that you can actually create the dynamic driving scenarios for testing of autonomous vehicles. So it's physically accurate, the simulation of the sensors. You have the virtual environments and the scenarios. In this case, you're seeing a car that actually can track people passing by, cars crossing, and actually the embedded software, it's getting the feedback from this virtual environment and testing all these scenarios in real time. And lightning, it's a very important thing when it comes to cameras and sensors. So you can actually simulate what the sensors are capable of seeing, what the light is impacting the sensor capabilities. So what you're looking is virtual testing with software in the loop and hardware in the loop simulation. On the next slide, I'm showing a little bit more detail on the sensor. So the sensor design and the camera optics are quite important. In this video that you're seeing, there's going to be a barrier and there's a motorcycle passing on the left. The camera won't be able to recognize the bike. You only see the obstacle in front of the person, in front of the car, sorry. So what happens is that you have a lidar in the back of the car that's going to say, well, there's another vehicle moving on our side, so we should brake, wait, and then move to the next lane. This way, you're not only guaranteeing your safety, but anyone else around you. Again, this all can be simulated with Optis capabilities in a virtual environment. More specifically to the sensors, the lidars, then you can see a couple videos that are showing the actual simulation of the optics part of the lidar. And then the video on top, I'm going to show how you trace and how it's being projected. And the video underneath, you'll be showing a little bit of let's say, the environment itself and how the positioning of the sensor will impact the range that you have. At the end of the second video, you can actually see the spectrum that actually is being recognized by the sensor based on the position you are applying it to. So all this new capability from Optis is now integrated with ANSYS products, bringing the what we call the closed loop on the simulation. Besides the environment, the traffic, the monitoring, and the sensors, we also have to take a very good look at the software itself. So autonomous softwares for vehicles or for any critical application requires a certified code. So that's what we call safety critical applications, or where mission critical applications, where any failure could be catastrophic and we could lose lives. So traceability and data management are mandatory. certified embedded code, it's also mandatory, and a safe architecture. So it's important to mention that it can also connect that safe architecture to neural networks and deep learning now. These new technologies that are coming in with the advancement of AI, they bring new challenges because it's very hard to control AI and guarantee its safety if it's making decisions on the go. So looking at the industry standard compliances, so you have ISO 26262, you have AutoSAR, you have the DO 178 and ARP 4754, which are examples from the defense and aerospace, automotive industry, and industrial. So how we tackle the embedded software challenge, we have a tool called ANSYS SCADE. As the name says, SCADE stands for Safety Critical Application Development Environment. The tool works specifically on a model-based environment where you can create the logic of the software that you're building. You don't work with very heavy loaded coding and debugging processes. You actually create the logic underneath the equipments and the autonomous vehicles you'll be looking at, and the code will be generated automatically. So the idea of SCADE is you get the architecture, you get the system level requirements, you build your design, and then from that, the generation of the code will be automatically, can be C or can be Ada, which are the leading codes used in the industry for that purpose. This certified code can come from different standards depending on your application. The examples that we gave for aerospace, industry, rail, and automotive. And the best part of it is that it also creates all the documentation for the certification process. So once you generate the logic, the code itself gets built, and then the documentation gets done. This part it's quite important, and you save up to 50% of the time of embedded software development for safety critical applications. It's quite a mouthful to say the SCADE applicability. So it's important to understand that when you're working through a whole certification process for a safety critical software, it can demand quite a fair amount of time, and there are reviews that needs to be done in the system itself, and each review will generate different code, will generate different certification papers. So this automated part actually saves a lot of time into the bureaucracy of the process. So last but not least on this part of safety, we need to talk about functional safety. So not only we need the software itself to be reliable and safety critical certified, we need it to be to test for every single environment and situation. So the ability to integrate a functional safety tool with the embedded software development and architecture will allow you to define the whole scenario and actually build the 2.5 billion road scenarios that we showed in the YMEO car before. So all of this comes together, closing the loop where you can actually do a functional safety analysis, define all the main risk scenarios, include all the scenarios in the virtual environment, and then let the embedded software do its testing, do its verifications, and debug it as necessary to make sure it's completely safe and completely reliable. So if you look at the whole scenario for functional safety, you have what we call our tool, it's called ANSYS Medini. So Medini Analyze, it's actually a functional safety tool. It can be used alone, standalone version, or it can be integrated in the whole system level simulation. So ANSYS is capable of actually integrating in the system simulation with a tool called Simplorer, the SCADE capabilities, which will build the embedded software and the displays if you require for the tool. You can integrate Optis for all the sensors, feedbacks, and all the data. You can have the virtual environment to actually test your embedded software, and you can also connect the 3D physics simulations for specific components that you need a higher level of reliability. All of that can be in a single environment, embedded of what we call a system level environment. where you can check the complete functional safety in a closed loop and get over with all your analysis, not necessarily doing everything physically. You can do most of your work simulated and then go to the physical analysis just for homologation purpose and regulations. So coming back to the autonomous systems, I will just pass the word now to Thomas Benke, which is our electronics expert. He'll talk a little bit about the components themselves and how we can better assess the main components that are involved in an autonomous vehicle. And thank you for the time.